This note video has a brief overview of beats and beat frequencies, sound wave characteristics, and factors that impact sound, as well as sonic booms. So let's get started. So a beat is when you strike something and it creates waves. So there's a pulse, a source of energy, if you will, and that then moves the medium, the thing the wave travels on, and that creates a wave. Now with sound, when you hit something or pull on something like a string, it then creates the waves. And so if you look here, this is showing what's called a beat frequency. So to give you an idea of what that looks like, we're going to listen to two different tuning forks. These two tuning forks are really close together in frequency, but not quite the same, and we're going to listen to the pattern that they create. So let's go ahead and play these two tuning forks in this demo. So this one's 250 hertz for the frequency. This one's a little lower at 238 hertz. They almost are identical. And that high-pitched ringing noise you hear where it sounds like it's loud and then nothing, loud and then nothing, that's a great example of wave interference, which was covered in that last video. So remember, when you have constructive interference, sound or the wave amplitude will get larger or louder. When you have destructive interference, it will get quieter. And so since these waves, the frequencies aren't the same, you have moments where they constructively interfere and then destructively interfere, kind of like this picture is showing right here, and that's why you get that pulsing sound. And we call that a beat frequency. And you can mathematically find the frequency by subtracting the two frequencies from each other. So for this one, we had 250 and 238. So that wave we just heard had a frequency of 12 hertz. So the net amount it's moving the air per second, when we hear that pulsing sound where it gets louder, quieter, had a frequency of 12 hertz. And so that is a beat frequency. Now, when we make a beat makes a sound. And so when we hear sound, sound depends on two things. So how quickly sound gets from one place to another will depend on the medium that it travels through. So remember, a medium is the thing that a wave travels on. So something like air, water, the wall, earth, basically any solids, liquids, like those are going to be mediums. And then temperature also plays a part. So the higher the temperature of the air is, or of a substance is, the faster that sound can travel through it. So the speed of sound on Earth typically varies from 333 meters per second to about 344 meters per second. That will be a value you're given if you're asked to use it in any problems using our wave speed equation. But just know it does vary based on temperature. And the exact equation is actually found down here at the bottom, where this T right here would be the temperature in degrees Celsius. And so we can actually calculate, as the temperature of a room increases and increases, how much faster that's making the sound travel. Now, a sonic boom happens when something travels faster than the speed of sound in air. So I have linked two videos in our classroom page, one showing a F-14 breaking the sound barrier. So again, once something flies, we call it Mach 1. That's the speed of sound. So like Mach 2 would be twice the speed of sound. Mach 3, 3 times the speed of sound. So once something exceeds the speed of sound, what happens is a pocket of air forms behind that object because it's going faster than the vibrations it's sending out to the air molecules making the noise around it. And so it makes this pocket behind it, and when that pocket collapses upon itself, it makes that pop or that boom noise. So check out those two videos. You're going to see one for that F-14, but I also included one for a volcanic eruption that happened in Papua New Guinea about 5 years ago. And you'll actually be able to see the energy coming off through the clouds from the explosion, the eruption, seconds before you hear it. So sound travels at about 340 meters per second, but light travels at 300 million meters per second. So light is going to travel faster than sound. So we're going to see the volcano erupt before we hear the volcano erupt. And so you'll actually see and hear that sonic boom made by the volcano. So I would definitely check those two videos out. They're really cool. Now, as far as music goes, pitch is the note that you hear. And so frequency is what determines how high or low a note is. So when something is coming towards you, the frequency of that note tends to go up in pitch, and it also will get louder in amplitude. So when you hear a sound moving towards you, the frequency should go up, the note you hear should go up, and it should get louder. Now, when that same sound moves away from you, it should get quieter, which means the amplitude of that wave got smaller, and the frequency, the pitch, should also get lower. So this is kind of what happens when there's a siren. So as it gets closer, louder, frequency higher. As it moves away, quieter, frequency gets lower.